Hi everyone. In this video, let us discuss trapping rain water. The given problem is given non-negative integers representing an elevation map where the width of each bar is 1. Compute how much water it can trap after raining. So the given thing is they have given a a kind of elevation map where width of each bar is 1. So this width is 1 and this is the height. The height of this bar is 1, the height of this bar is 2, and this is 3, like that. So this is a black shade, it is like a block, and the blue shade is the water. So height is like they given first at index 0, 0, 1, again 0, and 2, and 1, and 0, like that, 1 and 3. So like the same thing we can see here. Explanation: the above elevation map black screen is represented by array. In this case, 6 units of rainwater are being trapped. Yeah, if you see, the water can be trapped between two blocks only, right? Suppose you see here this one, and here this one. A height, suppose if you given height 420325, for this the output is 9. So let us understand how the algorithm is works here. We need to find at each bar the maximum water level. So if you look into the problem statement, so the here the approach is very simple. First, at each bar, like suppose I'm at this bar, okay, or I'm at this bar. So the water trap at this bar is 1, right? How we are getting this 1 unit? It is we are getting the simple logic is first, whatever first, what is the leftmost top and rightmost top? Suppose the rightmost top is, so here the leftmost top and rightmost top. The rightmost top, this is the height, and this is the left left maximum height. So the right maximum height minus left maximum height, if you minus, so you will get. So you need to check such a way. So suppose this is 3, and here your the leftmost height maximum is 2. So that means, so these two bars of the height is the bar. So that is at a particular bar, that is you can take like mat dot, you need to take the minimum of the left max comma right max. So you got the height minus, so here also the bar, the current height bar, suppose if you're pointing to here, the current height bar will be there, right? So for that you need to remove that height of I. So this is the basic algorithm if you follow. Let's discuss this again in a pad. So what I'm telling is we have a blocks. Let's see here. The blocks are like, suppose we have a block like this block, and this one, and maybe this one, and like largest bar and smallest. So what happens if you try to find the water? You want to, suppose you want to find the this this bar. Suppose I want to find what is the amount of water can found in this bar. So these are all the blocks I'll shade with. So whenever there is a rain, some water will come and accumulate, right? Suppose this here, here. This is blue is the water, this will accumulate it. So here we can nothing, because the right side is nothing, it will flow, the left side is also nothing. So suppose I am at this block, how can I find this amount of water? So suppose I am at this block, how can I find this amount of water? That is the case here. So I want to find this amount of water, first. So this is the height, right? The height, however, we will do minus that particular height. This is very clear. And before that you want to find this bar. How can you get this bar? Because it will trap until the left max, so we need to get the left max, and we need to check with the what is the right max and left max. So somewhere because this is the bar, right? So you need to get this height and this height, whatever minimum you will take it. So that's why I'm writing the left max height and comma right max math dot min. So like that you will get each at every bar. So the algorithm is this that simple. I'm taking I need to return that volume, right? So they're giving the height. So I'm taking the height, and first I'll calculate every time the left max and the right max. So building a left max array, that is so from I equals to 1 2, because 0 however we can't fill anything. So I equals to 1 2 I less than n I plus plus left max. I'm just keep on updating what is the left max. It's like here it is a 0, it here is 1, here it is 2, again the left max here is again 2. So we'll just updating the left max, keep on here like 2, again here 0. So here also 2 2, but here 3 updated. So suppose for the left max is 3, so we'll update here 3 at that bar. That's simple. And the similarly we do for the right, where the right also, the right, build the right max array. First I'm getting right max n minus 1, that is item n minus 1. And so already I will take this the rightmost height. After that I'll keep on calculate right max of I is math dot max of right max of I plus 1, to comparing the right side with the current height and keep on updating. So it is like suppose here 1, so here will 2, again here it is not 1, we'll update with 2, and here 2, here 3, so again here update 3. So at this point, suppose I want to check at this point, the left max is this one and the right max is this one. And after I'll calculate at every point, I'll calculate the water. So I equals 0, I less than 1, I plus 1, total water is that total water plus mat dot mean of left max of I comma right max of I minus height of I, and we'll return this water. So this is the algorithm. Let's run this code. So here the for this the so the test case is accepted. Let's submit. For here the so we are since following the approach like left max and right max, which is the time is order of n, order of n, order of n, n, order of n plus order of n plus, right? So order of n, and space is we're also using the space order of n. So we can use this by two pointers, where we can space also we can reduce by order of n. But if you do by brute force, the time complexity will be order of n square for this.